The second phenomenon that was not possible to be explained with the wave nature of light and supported the idea that light is quantized or moves in the form of discrete amounts of waves called photons is the photoelectric effect. When you shine light with a certain frequency on the surface of a metal, that light will be able to release the electron from the surface. It's not going to give it any speed. If we try to use a light with smaller frequency, we will not be able to eject any electrons. And based on that observation, we can actually make a prediction that the energy of the photon that you use in this case has to equal a certain minimum, because it has to overcome the binding energies that holds the electron to the surface of the metal. So that defines the binding energy of the electron, or sometimes what we call the work function, W, which is the energy that holds the electron attached to the atom or the metal surface. If you try to use a photon with a higher frequency, it's going to be able to eject the electron and give it more kinetic energy. And the kinetic energy that the electron will get in this case is going to be proportional to how higher the frequency is compared to the initial frequency or the threshold frequency. So we can mathematically describe this observation as that the energy of the photon used is equal to the sum of the binding energy of the electron and the kinetic energy that the electron will get after getting ejected. So the energy of the photon has to be large enough to be able to overcome the binding energy and give the electron a certain amount of kinetic energy. And increasing the frequency of the used light is going to only increase the kinetic energy of the ejected electron. It's not going to enable you to eject more electrons. It's just going to make the electron faster. So what can you do to eject more electrons? It was found that you actually need to shine light with higher intensity. You have to use light with more photons. So when you use light with more photons, you will be able to eject more electrons. The number of electrons ejected is proportional to the number of photons contained in your light. So these two observations supported the idea that light is a wave. However, it's a discrete wave that moves in discrete quanta called photons. You can explain the fact that the number of electrons ejected is proportional to the number of photons, as if each photon gets in, will collide with an electron and eject it. So it behaves like a particle in the fact that it actually collides with a particle. And we also observed that particles are also exhibiting a dual nature. So they are particles in the sense that they have mass. However, particles also move like waves. So any moving particle, according to Debroglie, will have an associated wavelength that is related to the momentum of that moving particle, or related to how fast the moving particle is. Associated wavelengths with a moving particle can be given by this formula right here. So it's going to equal Planck's constant divided by the momentum of the moving particle, which is a product of mass times velocity. It's actually really interesting because it means that the associated wavelengths can be modulated using the speed of the particle. So when you increase the speed of the particle, you should make the associated wavelengths much shorter. And that is actually the basis for electron microscopy, because you can accelerate a beam of electrons to a much shorter wavelength that allows you to picture much smaller objects and particles using the electron microscope, even down to a single atom. So we're gonna stop here, and next video we're gonna start learning how these understandings for the dual nature of light and particle allows us to understand the atomic structure in the next video.